So now we will learn the concept of determinants, so the determinant of a matrix. But first, let me just point out that for the matrix A, for this matrix A, which is composed of just one entry, A11, okay, the determinant of A is defined as the number A11 itself, okay? So for example, you have a matrix A with only a single entry, say 5, that the determinant of A is equal to 5. Okay? So that's for a 1 by 1 matrix. If your matrix is 2 by 2, like in the case of A here, okay, so A has 2 rows and 2 columns. To get the determinant, we will just do the following. Okay, first we multiply this diagonal, A11 and A22, and then we subtract from that the product of this off diagonal A21 and A22. So in short, the determinant of A in this case for a 2 by 2 matrix is simply the product of the diagonal A11, A22 minus the product of the off diagonals A21 times A12. Okay, so so far we have defined the determinant, or we have computed the determinant for a 1 by 1 matrix and a 2 by 2 matrix. The question is, what if the dimension of the square matrix is bigger than 2? So for example, you have a 3 by 3 matrix or a 4 by 4 matrix. It's a little bit complicated than the case of the 1 by 1 and the 2 by 2 matrix, because you compute the determinant uh, uh, and it is defined by induction. So later we will see what this exactly means. Okay, but for now, suffice that in order for you to compute the determinant of a 3 by 3 matrix, you need to look at several 2 by 2 matrices. Okay, the same thing with a 4 by 4 matrix. Uh, you need to look at the determinants of 3 by 3 matrices. Later we'll uh, know exactly what we mean by that. Okay, but first we need to define some terms. Okay, in order for you to compute the determinants. Okay, let's start with the case of a 3 by 3 matrix. Okay, first we define what's called the minor. Okay, the minor of Aij, of an entry Aij, which we denote now by Mij, okay, is the determinant of a submatrix obtained by deleting the ith row and the jth column of A. This definition seems to be abstract, but later by showing you some examples, we will see exactly what it means. Okay. Now, associated with entry Aij is not only the minor, but also what we call the cofactor. Okay. So for entry Aij, you can define a minor, but for entry Aij, you can also define a cofactor, okay, which is denoted by Cij, and this is defined as the following. The cofactor is just simply the minor for that entry, okay? So it depends on the address, okay? The minor, the cofactor is simply just the minor times -1 raised to I plus j. I plus j is the address, okay? So I is the row and j is the column, okay? So hopefully with some few examples, we will make this clearer. But so far, we have defined for now what a minor and a cofactor is. Okay, so let's go through some example. So this is the matrix A. Okay, matrix A is 2, 1, 3, 4, 5, 0, 6, 2, 1. Okay, that's the matrix A. Now, First, let us look for the minor of the entry A21, the minor associated with the entry A21. Okay, so this is A21 is the second row, the entry in the second row and first column. So it's this 4. Okay, so the definition of the minor is the determinant of the submatrix that you obtain by deleting the ith row and jth column associated with that entry. Okay, so what's the row number? The ith row is row 2 because this is located in the second row. So what you do is to delete the second row, okay, like this one, and the jth column associated with this entry over here is 1 because it's located in column 1. So you delete the column associated with that. Okay, so now you have a submatrix. Okay, so the submatrix, call it AS, okay, for lack of a better term. Okay, or just AA21, okay, meaning the submatrix associated with deleting entry, the row 21. Okay, so this submatrix is 1, 3, 2, 1. Okay, so you deleted this row and you deleted this column. You're left with the matrix, the 2 by 2 matrix 1, 3, 1, 3, 2, 1. Okay, so this is this matrix. Good. So what is the minor again? By the definition that we saw earlier, the minor is the determinant of that submatrix. Okay? So in this case, the determinant of the 2 by 2 matrix is just simply what? So like we saw earlier, first you have to get the product of the diagonal. This is this one, 1 times 1. And then you subtract the product of the off diagonal, which is 2 times 3. Okay? So this is 1 minus 6 is equal to negative 5. Okay? So this is the minor associated. This is the minor associated with 2, 1. Okay, so bear in mind that the minor depends on which row and column you delete. Okay, in this case, we have deleted the second row and first column. Okay, because we want to find the minor associated with the entry A21, which is M21. Okay, so we found the minor. Now the next step is to find the cofactor associated with that entry A21. Okay, so again, the cofactor is defined as simply the minor. Okay, this is the minor we've computed earlier. This is negative 5. And then you multiply it by negative 1 raised to the address, okay, the sum of the addresses. So negative 1 raised to 2 plus 1, where does this 2 plus 1 come from? It comes from the row number, which is 2, okay, and the column number, which is 1, okay, of the entry it is associated with. So notice that negative 1, let me just erase this. Notice that negative 1 raised to 3, okay, so negative 1 times negative 1 times negative 1 is negative 1. So this whole thing is negative 1, okay, because it has an exponent that is an odd number, okay. So negative 1 raised to 3 is negative 1. And then the minor associated with entry 2, 1 is negative 5. We have computed that before. So negative 1 times negative 5 is positive 5. Okay? So the thing to remember is the cofactor is just the minor, okay? But the sign of the cofactor depends on the address, okay? If the sum of the rows and columns of uh, the address of that associated entry is odd, then you multiply it by negative 1. So in this case, 2 plus 1 is odd, so it's a negative. Okay, so the negative 5 in the minor that you have computed before, you have to multiply it by -1, so now it becomes +5. Okay, so that's how you compute minor and the associated cofactor of the entry 821. Okay, now notice that notice that you have the dimension of the matrix. For example, in this case, is a 3 by 3 matrix. You have, in this case, 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 cofactors associated with each of the entries in the 3 by 3 matrix that we had before. Okay. Now, this is uh, this is rather surprising, but we can show that when you sum either a row or a column, so for example, this row, okay, you get this number, you get this number, you get this number, and you sum it, okay, so A11 C11 plus A12 C12 plus A13 C13, okay. So the entry times the entry in A11 times the cofactor associated at 1, plus the entry A12 times the cofactor associated with it, which is C12, and A13 plus A13 and multiply it with the cofactor associated with entry A13. Now this sum, okay, is equal to the sum of any other row or column. Okay, so for example, we take this column. Okay? This A12C12 plus A22C22 plus A32C32. Okay, take the sum of that column, of the numbers in that column. These are equal. Okay, this will give you the same number, and that same number is the determinant of that 3 by 3 matrix. Okay, so it's a little bit more complicated than the case of a 2 by 2 matrix, because in the 3 by 3 matrix you have to compute for the minor associated with each of the element, and then you have to compute for the cofactor associated with each element. Then you have to take the row sum or the column sum of the each of the rows of the entry times its associated cofactor. When you get that sum, you'll get a number which is common if you sum of any row or column, and that common number is the determinant of the 3 by 3 matrix. It's kind of convoluted. It's kind of tedious in a way, but that's how we define the determinant of a 3 by 3 matrix. Okay, good. Okay, now you may want to pause for a while and try to find uh, by yourself what is the determinant of this matrix A over here. Okay, now pause. Okay, now first, okay, first step in computing for the determinant is getting all the minors and the cofactors associated with this matrix. So first, we'll define the minors in A. Okay, this is also a 3 by 3 matrix. Okay, so how do you get m each of these entries in the matrix of minors? Let me just finish this one. Okay, how do you get M11 again? Okay, To get M11, you delete the first row and first column of matrix A. You delete the first row, and first column of matrix A, you're left with the matrix, this submatrix 5021. Okay? Okay. Now get the determinant of that. How do you get the determinant? You have to get the product of this diagonal. So 5 times 1 minus the product of the off diagonal, 2 times 0. So 5 minus 2, 5 minus 0 is equal to 5. Okay? So let's erase this and uh, put on this 5 over here. Okay? Great. Next step. How do you get this minor? Okay, the minor associated with the entry A12 of the matrix. Again, you delete the first row and second column of A. So delete the first row and the second column of A. Okay? And then you're left with this submatrix 4011. Okay? And then getting the determinant of this matrix is just simply 4 times 1, which is the product of this diagonal, minus 1 times 0, the product of this off diagonal. So here we have 4 minus 0 is equal to 4. Okay, so this is a little bit tedious, but we have to do this very carefully. Okay, good. Now, let's go to M13. Okay, this entry over here. We get this by deleting the first row and the third column. Okay? So deleting the first row and the third column in matrix A. So you're left with the matrix 4, 5, 1, 2. Okay? And then getting the determinant of this matrix, you just simply have 4 times 2, the product of this one, minus 5 times 1, which is this one. Okay? So this is 8 minus 5 is equal to 3. Okay? And so this is 3. Okay? Erase, erase. Okay, and then M21 over here, what you do is delete the second row and then the first column of matrix A. And now you're left with the matrix 1, 3, 2, 1. Getting the determinant of that is just simply 1 times 1 minus 3 times 2. Okay, so this 1 minus 6 is equal to negative 5. So this one is negative 5. Okay, and then M22 over here, M22 is just obtained by deleting the second row and second column. So you're left with the matrix 2, 3, 1, 1. Get the determinant of that, so it's 2. Okay, 2 minus 3, which is negative 1. Okay, so negative 1 over here. And then for this entry, I'll erase all of this. For this entry over here, I have to delete the second row and the third column. So I'm left with 2, 1, 1, 2. And so the determinant of that is 4 minus 1. This is 3. Okay, and then the next one, I have to delete this row and then this column. Okay, so the third row and the first column. And so I'm left with the matrix 1, 3, 5, 0. So 1 times 0 minus 5 times 3. So this is negative 15 over here. Okay, and then in the next entry over here, this one, you have to delete this third row and the second column. Okay, so you're left with the matrix 2, 3, 4, 0. Get the determinant of that. You have 2 times 0 minus 4 times 3, which is 0 minus 12 is negative 12. Okay, so this is negative 12. And then uh, last but not the least, we have this entry over here. This entry over here, where you delete the third row and the third column. You're left with the matrix 2, 1, 4, 5, and then get the determinant of that. So it's 2 times 5 minus 4 times 1. This is equal to 10 minus 4. It's equal to 6. Okay, good. So that's the matrix of minors associated with each of the entries in the matrix A. Okay, so the next thing is to obtain the cofactors associated with the entries. So in this case, cofactor associated with the matrix A is also A. There are 9 entries here because there are 9 entries in matrix A. Again, what's the definition of the cofactor of each of the entry? So cofactor is just negative 1 raised to the I plus j, which is the address, k times the minor associated with it. So in this case, for example, in the entry over here, it's just simply the minor, which is 5, times negative 1 raised to I plus j. What's I plus j in this case? I plus j here is 2 because it's located at the first row and the first column. So 1 plus 1 is equal to 2. So negative 1 raised to 2 squared is positive 1. So the sign doesn't change. Okay, so it's still 5. How about this entry over here? So it's 4, minor is 4, but now I plus j is equal to what? So it's the first row, this is the first row, and then the second column, okay? So I plus j, I is the first row, j is 2 columns, so 1 plus 2 is equal to 3. So negative 1 raised to 3 is negative 1. So the sign flips, okay? So this is actually negative 4. Negative 4, okay? This entry over here is 3 times negative 1 raised to, this is the first row, okay, and the third column. So 1 plus 3 is 4. So negative 1 raised to 4 is positive 1, okay? So the sign remains. So what you notice is that for addresses I plus j that sum into an even number, the signs don't change. If it sums to an odd number, the signs change. Okay? So in this case, in this entry, it's negative 5, but the address is 2 and 1, to row number 2 and column number 1, so the sign flips. So this is actually 5. Okay? This one is negative 1, and then the location is 2 and 2, row 2 and column 2. So the sign remains, so we still have a negative 1 here. And then in this entry, we have 3, and then the address is second row, third column, so it sums to 5. So negative 1 raised to 5 is negative 1, so the signs flip. Okay, so we have negative 3 over here. Okay. So in this entry over here, we have negative 15 as the minor, So it's located in the third row, first column. So 3 plus 1 is equal to 4. The signs don't change. It's an even number. And then here, negative 12. And this entry over here, negative 12. But the location is in row 3, column 2. So 3 plus 2 is 5. So the signs actually flip. So it's now positive 12. And here, in this entry, it's 6. The minor is 6. And the address is row 3, column 3. So 3 plus 3 is equal to 6. It's an even number, so the signs don't change. Okay? Great. So this is the cofactor uh, associated with each of the entries in the matrix A. Again, now, this is the final part. We have to determine what the determinant is. Determine what the determinant is. So how do you, again, compute for the determinant? Just pick any row or column. Okay? Suppose we pick this row in A. So 2, 1, 3. Okay? And then for each of the entries, here, we multiply it by the associated cofactors. Okay? So 2 times 5 plus 1 times negative 4, okay, plus 3 times, what's this one? 3, okay? So what's the sum of this one? So it's 10 minus 4, 6, plus 9. 10 minus 4, 6 plus 9 is equal to 15. Okay? Now, to check if you did everything correct, just pick any other row or column. Okay, uh, let's pick, for example, this one, the third column. Okay, and let's compute the determinant using the cofactors associated with that column. Okay, so we have 3 and 0 and 1. Okay, the associated cofactors are this one. Okay, so 3 times 3 plus 0 times, what's this one? Negative 3 plus 1 times 6. Now notice that if you do that, it's 9 plus 0 plus 6 is equal to 15. Okay? So notice that they have a common sum. I pick row 1 first, it gives me 15. I pick column 3, gives me 15. Now 15 is the determinant of this matrix. Okay? Still not convinced? Well, pick another arbitrary one. Say this one, row 2. So 4, 5, 0. And the associated cofactors are 5 for 4. So 4 times 5 plus 5 times negative 1 plus 0 times negative 3. Okay? So in this case, we have 4 times 5 is 20 minus 5, okay, is 15. So it's the same. So I'm pretty confident that we got this correct. Okay, so did you get the same answer? Okay, so this is the way to compute the determinant of a 3 by 3 matrix. Okay, so you see how tedious it is to compute for the determinant of a 3 by 3 matrix. Just imagine when you have higher dimension matrices. Okay, so the 4 by 4 matrix, for example, it's the same procedure. You have to compute for the cofactors associated with each of the entries, and it's bloody. Okay, so for a 4 by 4 matrix, its minors and cofactors are actually defined in terms of the determinants by a 3 by 3 matrix, which in turn are defined by determinants of a 2 by 2 matrix, which are the submatrices of the 3 by 3 matrix. So it's kind of convoluted, and that's how you find uh, the determinant of higher order matrices. Fortunately, we have computers now, so we don't have to do this manually. Okay, but of course, you have to learn this thing. Okay, so in this slide, we have a 4 by 4 matrix. It looks bloody. Okay, so we're tasked to get the determinant of this matrix. Good luck, but let's do this. Okay, so let's get the determinant in terms of the fourth row. Okay, so again, when you compute for the determinant, the any row or column, if you multiply it by its associated cofactor, you will get the common sum, and that common sum is the determinant. So for now, we'll use the fourth row. Why? Because it has zeros, so that will make it more convenient. So we only have to evaluate the cofactors associated with this, with 4 and negative 3 over here. Okay, so the determinant of the matrix A in this case is A41, C41, this entry times its associated cofactor, plus A42, this entry associated with its cofactor, A43, this entry associated with its cofactor, and A44, this entry associated with its cofactor. Okay, so we have 0 times C41 plus A42, C42 plus A43, C43 plus 0 times C44. Okay. Now, we'll try to find the cofactor associated with entry 42. Okay, this entry 42 and this entry 43. Okay, so let's start with 42. This cofactor over here. So cofactor is -1 raised to the address, which is 4 plus 2. And then the determinant of this submatrix when you delete the fourth row and the second column. So you're left with matrix 1, 4, 2, -1, 3, 5, 2, 1, 4. Okay? This is the matrix that's left. Okay? Now notice that in order for you to compute this determinant, you have to do the same thing all over again. Okay, like what we did with the 3 by 3 matrix earlier. But it's up to you if you want to do it. But let's take this by faith, and we'll see that the cofactor associated with entry 42 is 49. Okay, and then the cofactor associated with 43 is 7. Okay, and so the determinant is actually the entry. Let's erase this. The entry 4, 4 times its associated cofactor, which is 49, plus -3, and multiplied with its associated cofactor 7. So this is whatever, 4 times 49 minus 21 is 175. Again, you can compute it by yourself, or you can take it by faith. And so the determinant of this matrix A is 175. Okay? That's how you compute for the determinant of higher order matrices. Here are some theorems. The determinant of A transpose is the same as the determinant of A. Okay? The intuition is that since determinants are computed by getting the associated cofactors of each of the entries, whether it's row or sum, it doesn't matter. So in a transpose, the rows becomes the columns, or vice versa, the columns becomes the rows. Okay, so it doesn't matter there. So the determinant is the same for both a matrix A and its transpose. Okay, so if you have two matrices A and B, then you multiply it A A times B. Okay, and then you get the determinant of that. It's the same as getting the determinant of A first and then multiplying it with the determinant of B. Okay, so as an example of the first bullet point, so you see A here is 3, 1, 2, 4. A transpose is just getting the rows of A and making it columns. So 3, 1 is here. 2, 4, the second row becomes the second column. Okay, so Here, you can verify it. What's the determinant of A? It's 12. Okay, determinant of A is 12 minus 2. It's equal to 10. What's the determinant of A transpose? It's 3 times 4. It's 12 minus 1 times 2. It's 2. It's equal to 10. So the determinants are actually equal. Okay. Now, suppose we have two matrices A and B. Okay. So A is this one, uh, matrix 3, 1, 2, 4, and B is the matrix 2 by 2 matrix 1, 0, negative 3, 2 as entries. Okay? So if you compute the determinant of that one, so it's 12 minus 2, it's 10, and the determinant of B is 2 minus 3 times 0 is 0, so 2 minus 0 is 2. Okay, great. So you have the determinant of A is 10 and determinant of B is 2. Okay, now let's multiply A and B. You can do multiplication because the column, the dimensions of A and B conform, and they can be multiplied. So first, let's multiply it. Okay, and when you do the multiplication, you'll end up with a new matrix, a 2 by 2 matrix, 0, 2, with entries 0, 2, negative 10, and 8. Okay, now what's the determinant of that one? The determinant of that one is 0 times 8 minus negative 10 times 2. Okay? So it's actually negative of negative 20. It's 20. Okay? Now notice 20 is the same as just multiplying determinant of A and then the determinant of B. Okay, so that's just an illustration of the theorem that we had earlier. Now, in the next few slides, we will learn about the concept of a triangular matrix. But first, recall that the definition of the diagonal or the main diagonal. So the main diagonal is just, for example, in this matrix is just this entries. Okay, so these are entries with the same index. So A11, A22, A33, and so on and so forth. Okay, up to A and N. So for a 3 by 3 matrix, this is the main diagonal. And for a 4 by 4 matrix, this is the main diagonal. Okay, so what are triangular matrices? Okay, so a square matrix is said to be upper triangular, okay, upper triangular, if and only if the entries or the elements or the entries below the main diagonal are all zeros. Okay, so below the diagonal, okay, they are all zeros. On the other hand, it's lower triangular if the entries above the main diagonal are zeros. Okay, later we'll see an example. Matrix, a square matrix is diagonal if and only if the entries above and below, okay, both above and below are all zeros. Okay, these three matrices are called triangular matrices. Okay. So let's look at some examples. So again, the first matrix over here is an upper triangular matrix. By definition, upper triangular matrices are matrices where below the main diagonal, all entries are equal to 0. Okay, it looks like an upper triangular matrix because think of it like a triangle. I, I'm so bad at drawing, but look at this triangle above with with uh, above the main diagonal, below which the entries are all 0. Okay, it's up there. That's why it's upper triangular. On the other hand, the lower triangular matrix are can be thought of this way. So above the triangle are all zeros. Okay, or above the main diagonal are all zeros. So it's like a triangle in the lower part of the matrix. Okay, that's a lower triangle. So a diagonal matrix or a is a matrix where all entries above and below the diagonal are all zeros. Now these are special matrices. Why? Because we have a theorem here which says that the determinant of such triangular matrices, okay, the determinant of any triangular matrix is just what? Is the product of its diagonal entries. Okay? So if we have a matrix A like this one, which is an upper triangular matrix, okay? So when you get the determinant of that, we, for example, uh, we get the we get the cofactor associated with the entry A11. So it's negative 1, 2 over here because it's 1 plus 1. And then the determinant of the submatrix when we delete row 1 and column 1. Also, it's A22, A23, 0, and A33. Now, this determinant is just uh, A22 times A33 minus 0 times A33 is 0. Okay? So that's the cofactor associated with element A11. Now the next entries here are just zeros because these are zeros. So 0 times its associated cofactor is just 0. Okay, so it all boils down to this. The determinant all boils down to this number. Okay, so it's A11 times this determinant. It's A22 times A33 minus 0. So it's A11 times A22 times A33. Okay, so what's this one? So A11 times A22 and A33 is just the product of the entries in the diagonal. Okay, so that's an illustration of the proof of the theorem. So automatically, if you have a triangular matrix, you don't have to do the long-winded calculation of the determinant. Just look at the diagonal entries, and then you multiply all the entries, and that's your determinant. Okay, makes your life easier. Okay, now we're going to an important part of this section, which is computing for the inverse of a square matrix. Okay, so the definition of an inverse, okay, is simple. So if you have a square matrix A, again, this only works with square matrices. So a square matrix is a matrix that has uh, the same number of rows and columns. Okay, so that's a square matrix. So suppose you have a square matrix A, okay, and another square matrix B, okay, same order, okay, same dimension. Now, if both A and B, the product of A and B, okay, is equal to, this should be bold I. You should equal the identity matrix. Okay, again, to recall, the identity matrix is just, for example, of order 3, it's just a matrix with 1 in the diagonal and 0 elsewhere. Okay, so this is the identity matrix. Okay, so if you multiply A and B, and the resulting matrix is a identity matrix, okay, then B is an inverse of A, and it's also the same. So if you multiply B to A, and then you get the inverse, you get the identity matrix, A is also an inverse of B, and vice versa. Okay, so for example, we have uh, matrix A over here and matrix B over here. Okay, so when I multiply AB, okay, so how do you get this entry over here? It's just the inner product of the first row and the first column. So that inner product is 1 times 0 plus negative 1 times negative 1. Okay, so this is just 1. Okay, so this is this entry over here. How about this entry over here? It's the inner product of the first row of A and the second column of B. So it's 1 times 1/2, okay, plus -1 times 1/2. So it's 1/2 minus 1/2 is equal to 0. That's why you have a 0. And just to finish up, so we have this entry over here. How do you compute it? Just get the inner product of the second row and then the first column, second row of A and the first column of B. So it's 2 times 0 plus 0 times -1 is equal to 0. And then finally here, this is obtained by getting the inner product of the second row and then the second column of B. Second row of A and the second column of B. So it's 2 times 1/2 plus 0 times 1/2. Okay, so 2 times 1/2 is equal to 1. So in the end, what you get is this matrix with ones in the diagonals and 0 elsewhere. So this is the identity matrix. Okay, so in the same manner, if you do this multiplication of B and A, you'll also wind up with the identity matrix. Okay, so A and B are inverses of each other. Okay, so this is a remark. From the definition, it is clear that B is the inverse of A and vice versa, A is the inverse of B. Okay, now when you have an inverse, of a matrix, that inverse is unique to that matrix. Okay, why is it so? So for instance, in the definition, okay, we have two matrices A and B, okay, over here, which is when you multiply them, they equal the identity matrix, and so B is an inverse of A. Okay. On the other hand, if it's true that C is an inverse of A, then this also should hold. Okay. So if you multiply A by another matrix C, it should yield the identity matrix, so on and so forth. Okay. So is B, okay, is B the same as C? Okay? Meaning if B and C are the same, then the inverse of A is unique. Okay? In this case, it is because, for example, we start with B. Okay? Now, in this next part, we just post-multiply B by the identity matrix. You know that if you post-multiply or pre-multiply a matrix by the identity matrix, you recover the matrix, the square matrix itself. Okay? So this is true. This statement is true. B is equal to B multiplied by the identity matrix. But then the identity matrix, okay, by assumption is equal to AC from this part. Okay, so we just substitute I. Okay, so substitute this one. So therefore, this is the AC over here. Okay, okay. By the associative property, we can shift the parenthesis to B A, okay, B times A, and then C is post multiplied. Now B times A by our assumption is equal to I. Okay? This one. Okay? So therefore we can write it as I times C. Okay? Now the property of the inverse is that if you multiply everything by any matrix by the inverse, you recover the matrix itself. So I times C is equal to C. Now, what does this statement tell you? In the end, B is equal to C. Okay? B is equal to C. So, so this means that if two matrices are inverse of a matrix A, it is true that they should be equal or they should be the same matrix. So therefore, the inverse of A is a unique matrix. Okay? So there cannot be two inverses for a particular matrix. But not all matrices have inverses. Okay? So for example, this matrix where we have 1 in all of the entries. Okay, so 1, 1, 1, 1, a 2 by 2 matrix with ones in them. Okay, now suppose B is a matrix, B1, 1, where entries B1, 1, B2, B1, 2, B2, 1, and B2, 2. Suppose this is an inverse of A. Okay, suppose this is an inverse of A. Then what must be true? If B is an inverse of A, when we multiply A and B, the matrices A and B, it should what? It should yield the identity matrix. Okay? Okay? That is true if B is an inverse of A. But now notice that for that to be true, you have to compute for each of these entries. Okay? Now let's do this entry over here. This entry over here. How do you get this entry over here? Well, you get the inner product of the first row and the first column of matrices A and B respectively. So it's 1 times B11 plus 1 times B12. Okay. Sorry. Uh, should be should be the inner product of first row and first column, and so it should be uh, 1 times B11 plus 1 times B21. Okay, is equal to 1. This entry over here. So this is this part over here. Okay, then let's look at this entry over here. How do we obtain that entry? This entry. So it's obtained by getting the second row. Okay, the second row of A, the inner product of the second row of A and the first column of B. So it's 1 times B11. Okay, so the second row of A and the first column of B plus 1 times B21 is equal to 0. Okay, so this is this entry. Now, notice that B11 and B21 are the same numbers. Okay, so it's impossible that the sum of those two numbers can be simultaneously 1 and 0. Okay, it's just impossible. Okay, so for matrix A, no inverse exists because there is no matrix that would satisfy this property that if you multiply it with matrix A, it will yield the identity matrix. Okay, good. So the lesson is that not all matrices are invertible. Okay, so just for notation, uh, when we say inverse, okay, we denote it by putting this -1 here. Okay, so if matrix A, if we have a square matrix A, its inverse is a -1. Okay, or you read that as A inverse. Okay, A inverse. And so, what's true if A inverse is the inverse of A, then if you multiply A and A inverse, it should yield the identity matrix. Or if you pre-multiply A inverse with A, it should yield the identity matrix. Okay, just uh, another notation or definition. The square matrix is non-singular, okay, if and only if it has an inverse. Okay, so a matrix A is non-singular if it has an inverse. So the matrix that we saw before, where we have matrix 1, 1, 1, 1, this doesn't have an inverse. So this is a singular matrix. Okay, singular. So a matrix that has an inverse is called a non-singular matrix. Now here's a useful theorem. So a square matrix is non-singular, or it has an inverse, if and only if what? If and only if its determinant is non-zero. Okay? So if you have a square matrix and you compute the determinant to be zero, then it's singular. Okay? Otherwise, if it's non-zero, if the determinant is non-zero, then that matrix can be inverted, or you can find an inverse of that matrix and it's non-singular. Okay, so recall the example that we had a while ago, where you have this matrix A with entries 1, 1, 1, 1. Okay, so we said earlier that this matrix has no inverse. So what is the determinant of this matrix? Okay, so that A, the determinant of A is obtained by multiplying this one is 1 minus the off diagonal 1, 0. Aha. Okay, so the determinant of A is 0. Therefore, this matrix is singular. Therefore, this matrix doesn't have an inverse. Okay, so it must be true that the matrix has to have a non-zero determinant for it to have an inverse. Okay, now we're climbing to the top slowly. So uh, let's now actually find the inverse. Okay, let's find a method to find the inverse of uh, a matrix. Now recall that we have shown a while ago how to compute for the cofactors associated with each entry of a matrix A. So we now define what's called the cofactor matrix. It's similar to the it's actually what we did a while ago. So the cofactor matrix of A, matrix A, is just the matrix of the cofactors of A. Okay, the cofactors. Recall the cofactors is just -1 times I plus j times the minor, okay, associated with the entry. Okay, good. So each entry is computed this way. So this matrix is called the cofactor matrix of A. Okay, and the cofactor matrix of A has the same dimension as the matrix A. Good. Because it's associated with each of the entries in matrix A. Okay, and we now define what's called an adjoint. Okay, the adjoint of the matrix A, okay, adjoint A, is defined as simply the transpose of this cofactor matrix. Okay, so the adjoint of A, okay, is just simply the transpose. So all these rows becomes columns. Okay, so C11, C12 to C1n. Okay, this is C21, C22, C2n. Okay, and here we have Cn1, and then all the way to Cnn. Okay, so just take the rows of the cofactor matrix and make it the columns, and then you have the adjoint of A, which is simply just the transpose of the cofactor matrix. Okay, I know this is like overwhelming, but uh, the point is that you can compute for the inverse of A. Okay, if A is non-singular, meaning if the inverse exists, then you can compute for the inverse. You can find the inverse of A by simply dividing the adjoint of the matrix A. Each entry you divide it with by the determinant of A. Okay, so first you look for the adjoint of A, and then for each of the entries in the adjoint of A, you divide it by the determinant of A. Now this is where the concept of a non-vanishing determinant comes into play. Because if the determinant of A were 0, if it's singular, then this would not exist. Okay? So 1 over 0 would not exist. So this is a scalar. Okay? Good. So that's how you find the matrix which is the inverse of A. Okay? Good. Okay. So as an example, let's do this. Suppose you have this matrix A. This matrix is a 3 by 3 matrix, 3, 0. Oh, sorry. This matrix is a 3 by 3 matrix uh, with entries 3, 0, 1, 2, 1, 4, and 1, 0, 1. Okay? The first step is actually determining whether this matrix has an inverse. And how do you determine it? Well, first step is to check the determinant. Okay? Is it non-zero? Okay? Then the second step is to obtain the cofactor matrix. Once you have the cofactor matrix, you get the transpose of that. So the transpose of the cofactor matrix is called the adjoint matrix. Okay? Then once you find the adjoint matrix, you just divide each of the entries of the adjoint matrix by the determinant of A. And that's the inverse. Okay? So these are the steps on how to find the inverse of the matrix. Okay? Let's do this. 3, 0, 1, 2, 1, 4, 1, 0, 1. Okay? So matrix A is 3, 0, 1, 2, 1, 4, and what? And third row is 1, 0, 1. Okay. 1, 0, 1. Okay. First, you get the cofactors of A. Okay. So this is a little bit tedious, but let's go through this very carefully. So let's get the cofactor of the matrix associated with A. Okay? So this is also a 3 by 3 matrix. Okay? How do you get the entries of this 3 by 3 matrix? So let's get C11 first, which is this one. Okay? So C11 is just simply negative 1, 1 plus 1 times the minor of 1, 1, which is obtained by deleting the first row and first column. So it's just the determinant. The minor is just a determinant of the submatrix where you delete the first row and first column. So it's 1, 4, 0, 1. Okay? Okay? So this is this. Okay? This part over here. Now when you do that, you have 1 minus 0. It's equal to 1. And this is equal to 1. And this one, since it's the exponent is an even number, it is positive 1. So we have 1 here. Okay? So let's just do this. So the first entry here is C11 is 1. Okay? This entry over here, using the same process, is this one, negative 1, and then the exponent is 1 plus 1 plus 2, which is equal to 3. And the determinant of the submatrix when you delete the first row and then the second column. Okay? So it's 2, 4, 1, 1. Okay? And so on and so forth. So if you compute that, this determinant is 2 minus 4, it's negative 2. Okay? But you have a negative 1 here, so negative 1 times negative 2 is positive 2. So let's just, you can look at this one. So this is how you compute each of the entries in the cofactor matrix. Okay, so let's just complete this. It's 1, 2, negative 1, 0, 2, 0, okay, negative 1, negative 10, and 3. Okay, so this is the cofactor matrix, which is just simply the cofactors The entries of the cofactor matrix are the cofactors associated with each of the elements in matrix A. Great. Okay, so this is the cofactor of matrix A. Now, how do you get the adjoint? The adjoint is just simply the transpose of this cofactor matrix. So again, the transpose of cofactor matrix, the cofactor matrix is just, you just get the row and make it the columns, okay? So this first row is 1, 2, negative 1, you make it the column, 1, 2, negative 1. The second row is 0, 2, 0. The second row will be the second column, 0, 2, 0. And the third row will be the third column, negative 1, negative 10, and 3. Okay? Oh, it's here. Okay, so that's the adjoint of A. Okay? So the last part is um determining the inverse. Okay? So that theorem or that result a while ago says that the inverse of A is just simply the adjoint of A, okay, divided by the determinant of A. Okay. So how do you we know this is just this adjoint, but the determinant of A is computed by what? Just get the original matrix A and then just multiply the any row or column with its associated cofactor, and then you'll get the determinant. Okay, so let's go back. What again is matrix A? I forgot. 301, 214, 101. 301, 214, 101. Okay, A is 301, 214, 101. Okay, how do you get the determinant of A again? So let's take the first row, for example, 301. So 301, and then you multiply each entry by its cofactor. So 3 times 1, this is this one, 0 times negative 2, and then it's not negative 2 but positive 2, and then 1 times negative 1. And then you sum all of that, so it's 3 plus 0 minus 1 is equal to 2. Okay, so this is the determinant 2. So you divide all entries in the adjoint by 2. Okay, so it's 1 over 2. So the adjoint is this one. So divide 1 by 2, you get 1 half. 0 divided by 2 is 0. Negative 1 divided by 2 is 1 half. Negative 1 half. 2 divided by 2 is 1. 2 divided by 2 is 1. Negative 10 divided by 2 is negative 5. Negative 1 divided by 2 is negative 2. 0 divided by 2 is 0. And 3 divided by 2 is is positive 3 halves. Okay, so there you have it. We claim that this is the inverse of A. Okay, now how can you make sure that this is the inverse? This is the actual inverse. So A is, again, 301, 214, 301, 214. Is this right? How do you check if this is truly the inverse of A? Well, you can multiply A and A inverse, and they should be equal to the identity matrix. Okay, so let's multiply 301, 214, 101 with negative 1 half, 0, negative 1 half, and then 1, 1, negative 5, and then negative 1/2, 0, 3/2. Okay? So if you multiply that, the entries are 3/2 minus 1/2. Okay, this is 2/2, this is 1, and then this entry is 3 times 0, 3 times. So this entry here is 3 times 0, 0 times 1 plus 1 times 0 is 0. And then the third entry over here is this one and this one. So 3 times negative 1/2 is negative 3/2 plus 0 times negative 5 plus 1/2. So negative 3/2 plus 3/2, I mean, this is 3/2, so this is equal to 0. And you can verify that this indeed will result in the identity matrix. So in this case, A, this is the matrix A, and A inverse are, when you multiply it, will become the identity matrix. And so therefore, A inverse is actually the inverse of